project, we work with the fashion minutes dataset, which is a collection of 70,000 images of clothing items, including 60,000 images for training and 10,000 for testing. The image are grayscale 20 x 20 pixels and divided into 10 different categories, such as t-shirt, trouser, pullover, dress, coat, sandal, shirts, sneaker, bag, and ankle boots. So we started by importing the fashion minutes datasets from the Keras library and explore the dimensions and length of the training and testing sets. So we also visualize some of the image from the datasets using the Matplotlib library. And next, we created a sequential model using the Keras library and add the 3 layers. 2 hidden layers with 512 and 128 neurons, and an output layers with 10 neurons using and softmax activation function. So we chose to use the softmax activation function on the output layers because it provided the probability for the 10 different categories that the image could belong to. So to prepare the data for training, we flattened the image from 20 x 20 to 1 column with 784 neurons and normalized them by dividing them by 255. So we also compiled the model using 2 different settings, Atom Optimizer and Sparse Categorical Cross-Entropy Loss, and RMS Plot Optimizer with Categorical Cross-Entropy Loss. So to see the difference in the achieved accuracy and loss, and then we train the model using the fits method and set the equal to 10. So finally, we evaluate the model's accuracy and loss on the test sets and found what we did not have overfitting. So here we go. Here's a code that we're gonna running through. Okay, it's gonna take time still loading. So here's the first question. The training image have dimension of 60,000. 20 x 28 training labels have the dimension of 60,000, and the test image have the dimension of 10,000. 28 x 28, and the test label have the dimension of 10,000. Escape, running through. So we're gonna plot the image of the index 5 in the training datasets using the Matplotlib library. So here's the code to do so. So in order to fit the image data into a neural network, we need to reshape it from a 20 x 20 matrix to the flex 1D vector with 784 elements. This is called flattening the data. So this is the following code. It's going to show 2 methods for the flattening data. So the first method, we are using the reshape function, and the second method that we use is flatten layers in the Keras. And also, um, in the question 13, so we're normalizing the image data. It's important to ensure that each pixel value falls within a certain range, 0 to 1. This can help improve the training performance of the neural network. So this is the following code. So the first method we use is divided by 255, and using the num_b. And the method 2, we're using the built-in normalize function in Keras, and this is going to be the following code. So here's question 16. So the last layers of the neural network should have the same number of the neurons as the number of class we are trying to predict. So in this case, we have 10 classes. We use the softmax activation function for the last layers because it can help convert the output of the neural network into probability value for each class. So under the hood, the softmax function takes the output from the previous layers and scale it so that the sum of all the values is equal to 1. So this ensures that the output value can be interrupted as a probability. So here's the code adding to the last layers. And then we need to compile the neural network before training it. So this involves specifying the loss function optimizer and the evaluation matrix to use during the training. So the first setting we use is the Atom optimizer. Sparse categorical, quotient, trophy, loss function, and accuracy as the evaluation matrix. So the second setting uses the RMS prod optimizer, categorical, quotient, trophy, loss function, and accuracy as the evaluation matrix. So these settings define the way that our model is trained and evaluated. The choice of optimizers and loss function can significantly impact the performance of the model. So after the compilation, we train the model on our training data using the fit. Using the fit method, so we set the number of the epoch to 10, which means the model will go through the training data 10 times during the training process. The fit methods using a training loop that update the model's parameters with each batches of the training data, and then evaluate the model's performance on a separate validation set. Lastly, so to evaluate the performance of the model on the dataset, test data, we use the evaluate method. We use the evaluate methods with the test data and the label. These methods return the loss and accuracy of the model on the test data. So overfitting can be identified if the model performs significantly better on the training data than on the test data. So in our case, we do not have significant overfitting as the accuracy on the test sets is close to the accuracy on the training sets. Yes, pretty much that's it.